Hello, welcome to another module in this massive open online course. All right. So we are looking at the properties of the region of convergence of the Laplace transform. Let us continue this discussion. If xt is a two-sided signal, on the other hand, if xt is a two-sided signal, which implies xt is non-zero for the entire range, that is minus infinity less than t less than infinity, that is it looks something like okay, it is a two-sided signal. Okay. This is the time axis, okay, and this is x of t is non-zero. Then the ROC is of the form sigma 1 less than real part of s less than sigma 2, where sigma 1 comma sigma 2 are the real parts of two poles of x of s. Where sigma 1 sigma 2 are the real parts of two poles of x of s. Thus the ROC is the vertical strip thus ROC equal to vertical strip between the lines real part of s equals sigma 1 comma real part of s equals sigma 2. So the ROC is basically a vertical strip, okay, and this you can check this as follows, that is basically if you look at this again, let me just draw this. So you have sigma, you have j omega, you have your sigma 1, you have your sigma 2, the real parts between these two poles, okay, and therefore the ROC will be this vertical strip. This is your ROC. For instance, let us take again a simple example. This I think is best illustrated using an example. For instance, if you take xt equals minus e raised to 2t u minus t, okay, minus e raised to 2t u minus t, correct, and plus e raised to minus 3t ut, then the Laplace transform. Now look at this is a two-sided signal, okay. So this you can you can check, because u minus t is non-zero for t less than 0, ut is non-zero for t greater than 0. So this is a two-sided signal. This and the Laplace transform xs you can verify, that is given as 1 over s minus 2 plus 1 over s plus 3, and the poles are two comma minus 3, and the ROC will be basically, you can see it is the intersection of the ROCs of the both signals, that is real part of s greater than minus 3 intersection real part of s less than 2, that is the intersection, and which implies the ROC is basically minus 3 less than real part of S less than 2. So, this is basically your final ROC, and therefore, it includes the strip between minus 3 and 2, and this can be simply illustrated as follows. This is sigma, this is j omega, and you have minus 3 sigma equals minus 3 here. This is one pole, and you have sigma equals 2 here. This is another pole. This is the other pole, and the ROC is the strip between these two. ROC is minus 3 less than real part of S less than 2, and any other poles can only lie outside the ROC. So, you can have poles which are outside, only outside the ROC, okay? And this is basically a vertical strip. So, this is the ROC, that is sigma 1 less than, it is the form sigma 1 less than real part of S less than sigma 2. This is basically the ROC, and the ROC in this example is minus 3 less than real part of S less than 2. So, let us look at the partial fraction expansion. The partial fraction of expansion, that is, if x, we have xs equals some constant k times s minus z1 times s minus z2 into s minus zm divided by s minus P1, that is Z1, Z2, Zm are the zeros, S minus P2 into S minus Pn, where M, P1, P2, Pn are the poles, and M is less than n. Remember, when M is less than n, this is known as a proper rational expression or a proper rational function. So, if it is a proper rational function, I can express, that is, implies as a proper rational function. If this is a proper rational function, then I can express xs as the sum, and simple pole case, we are assuming all the poles are distinct. That is, we have simple poles. That is, no two poles are such that pi equals pj, that is, all poles pi not equals pj. So, we have all the poles are distinct. So, for the simple pole case, all poles are simple, which means all poles are basically distinct, and for that scenario xs can be expressed as C1 by S minus P1 plus C2 by S minus P2 plus Cn by S minus Pn, where the coefficient Ck is given as S minus Pk times xs evaluated at S equals Pk. Okay, so, this is the partial fraction expansion of xs and Ck is the coefficient, kth coefficient, all right, in the partial fraction. This is the coefficient in the partial fraction expansion of xs. This is the coefficient in the partial fraction expansion of x's. Okay. So, what we have is a partial fraction expansion for the case where m is less than n, alright, that is the degree of the numerator polynomial is strictly lower than the degree of the denominator polynomial. This is a proper rational function, xs is a proper rational function, alright. In this case, when express using its partial fraction expansion, that is the sum C1 by S minus P1 plus C2 by S minus P2 so on, and Ck, the coefficient of the kth term, is given as S minus Pk times xs evaluated at the pole S equals Pk, okay, and all the poles are assumed to be simple, that is there are no repeated poles, okay. So, all the poles are distinct, Pi not equals Pj, okay. Now, for the multiple pole case, now for the multiple pole case, xs in denominator has a factor of form S minus Pi raised to the power of r, and in this scenario we say that the pole Pi has a multiplicity of r, okay. So, this implies pole Pi has multiplicity equal to r, and therefore, xs will have terms of the form, the partial fraction expansion of xs will have terms of the form lambda 1 divided by S minus Pi plus lambda 2 divided by S minus Pi square plus lambda r divided by S minus Pi raised to the power of r. So, these are the terms corresponding to S minus Pi these are the terms corresponding to pole Pi, okay, and you will have the rest of the terms corresponding to other poles, terms for pole Pi which has multiplicity r, okay. So, these are the terms. So, there will be r terms corresponding to the pole Pi, alright, lambda 1 by S minus P1 Pi, lambda 2 by S minus Pi square, so on up to lambda r divided by S minus Pi raised to the power of r, where r is the multiplicity of the pole Pi, and the coefficient lambda r or lambda r minus k is evaluated as follows. We have the expression for lambda r minus k, that will be equal to 1 over k factorial. So, this expression will be equal to 1 over k factorial dk d raised to s power k s minus Pi to the power raised to the power of r into xs evaluated at s equals Pi, okay. So, this lambda r minus k, let me just write it again once again clearly, lambda r minus k equals 1 over k factorial times d to the k ds to the k s minus pi raised to the power of r x to the power of x s evaluated at s equal to pi. Okay. Evaluated at s equal to pi. Okay. So, this is basically the expression coefficient of, remember, coefficient in the partial fraction expansion, coefficient in partial fraction expansion of xs. Okay. This is the coefficient in the partial fraction expansion of the rational function, the rational for xs, which is the rational function of s. Okay. Alright, so that takes care of various scenarios, that is when you have simple poles as well as multiple poles. Okay. Now, let us look at the Laplace transform properties for LTI systems. Okay. That is the next aspect, the Laplace transform and its application for LTI systems. Okay. So, let us look at Laplace transform for LTI systems. Now, for an LTI system, consider an LTI system given by impulse response ht. Okay. Okay, so this is LTI system. ht xt equals the input and yt equals the output of the LTI system. Then we know that the output yt of an LTI system is a convolution of the input xt with the output it is a convolution of the input xt with the impulse response ht of the LTI system. Therefore, the output impulse response, remember convolution in the time domain is a product in the transform domain, that is a Laplace domain. Therefore, since we have yt equals xt convolved with ht, remember this is your convolution, and therefore, once we take the transform, the Laplace transform ys will be the product of the Laplace transforms of xs term hs, and in fact this implies that hs equals ys divided by xs, and hs, this quantity is known as, this has a very important role in the analysis of LTI systems, this is known as the transfer function. This is known as the transfer function. This is known as the transfer function of the system. Okay. So, hs, which is the Laplace transform of the impulse response, remember hs is the Laplace transform of the impulse response ht, this is known as the transfer function, and this characterizes, is a fundamental aspect property of the system, it characterizes the behavior of this LTI system in a very fundamental fashion. Okay. So, ht, remember ht has Laplace transform. So, hs is the Laplace transform of the impulse response. So, this is So, this is the Laplace transform of the impulse response of the LTI system under consideration. Further, now let us look at other properties of the LTI systems, and from the perspective of the Laplace transform. So, other properties of LTI systems. So, other properties of the LTI systems. Let us look at some other properties of the LTI systems. Now, let us look at causality. Now, for a causal system, remember we have Ht equal to 0 for t less than 0, which implies basically, if you look at this basically implies that Ht is a right handed signal. This basically implies Ht is a remember we have Ht of the form, correct, we have Ht equal to 0, correct, Ht equal to 0 for the impulse response has to be 0 for t less than 0, correct. That is the property of the causal, that is the property of the causal, that is the property of the causal LTI system, that is Ht equals 0 for t less than 0, which implies Ht is a right handed signal, which implies the ROC of Ht. Now, from the properties of the ROC, therefore, the Laplace transform Hs must have ROC which is of the form real part of S is greater than sigma max. Okay. So, the ROC, this implies the ROC of Hs is of form the real part of S is greater than sigma max. Remember, this follows from the properties of the ROC, that is, since Ht is a causal system, since the LTI system is a causal system, it must be the case that the impulse response is non-zero for t less than 0, which implies that it is a right handed signal, and therefore, the ROC of the ROC of Hs, which is the impulse response of Ht, which is the Laplace transform of Ht, must be of the form real part of S greater than sigma max. Okay. Now, let us look at stability of the LTI system. Now, let us look at the stability of the LTI system. Now, it is Bibo stable remember bounded input bounded output stable if integral minus infinity to infinity magnitude h of t less than infinity. This implies that ROC contains the j omega axis. That is, if you look at the S plane, y axis is the j omega, this is the, so this is basically your S plane. Now, whatever is the ROC must contain the j omega plane. If the system is stable, ROC must contain the j omega axis. that is, this can be seen as follows. Okay. If you look at magnitude of h of j omega, that is equal to integral minus infinity to infinity h of t e raised to minus, that is, if you substitute s equals j omega, magnitude of h of j omega is integral minus infinity to infinity h of t e raised to power minus j omega t dt, which is less than, that is, in magnitude of the integral is less than or equal to the integral of the magnitude, which is less than or equal to, therefore, integral h t integral e power minus j omega naught omega t dt, but magnitude of e power e raised to minus j omega t is 1, which means this is equal to integral e power minus infinity to infinity h of t dt. Okay. So, magnitude of h of j omega is less than or equal to this, which means, therefore, if this is finite, if this quantity is finite, which implies if this is finite, implies if this quantity, if integral magnitude integral minus infinity to infinity magnitude h t dt is finite, this implies h of j omega equals a finite quantity, okay, less than infinity, which implies j omega is element of j omega belongs to the ROC. So, argument is the following, that is, h of j, magnitude of h of j omega is strictly is less than or equal to integral minus infinity to infinity magnitude h of t dt, which is a finite quantity. Therefore, magnitude of h of j omega must be a finite quantity, which implies the Laplace transform must converge for s equal to j omega, which implies that j omega belongs to the ROC of the Laplace transform. Okay. So, implies j omega axis belongs to ROC of the Laplace transform, that is h of s. Okay. And finally, Laplace transform, that is a transfer function of the LTI system described by the differential equation. We have the transfer function of the LTI system described by the differential equation. Described by a differential equation, that is, I have some k equals 0 to n a k d raised to k y t dt k, that is equal to some k raised to 0 to m b k d raised d k x t dt, okay, d to the d k d to the k x t over dt k. Now, we know from the properties of the Laplace transform that y t has Laplace transform y s, implies, so y t implies d raised to dt, remember dy t over dt has Laplace transform s y s. In fact, this implies progressing this way, we can show, one can show that d raised to k yt or dtk, or for that matter d raised to k yt or dtk has Laplace transform s to the power s raised to k ys. Similarly, d raised to k xt dt over dtk, all right, the kth order derivative of the signal xt with respect to time has the Laplace transform s to the power of k xs. Okay. So, substituting this we have, so from the differential equation it follows that we have summation k equal to 0 to n a k s k s raised to k ys equals summation k equal to 0 to m b k s raised to k xs. So, implies taking ys common on the left, xs common on the right. So, ys by xs, if you look at this, this is equal to summation k equals 0 to m b raised to k x k s k divided by k equal to 0 to n a raised to a k s raised to k, and this is a transfer function. In fact, we remember we said Hs is defined as the impulse response, that is the Laplace transform of the output divided by the Laplace transform of the input. So, this is the transfer function of the system. This is the transfer function of the system, and remember this is a rational function. Okay. You can clearly see this is a rational, you can clearly see that this is a rational function. Okay. Okay. So, all right. So, basically that completes our description of the definition and the properties of the Laplace transform. So, for with this what we have done is we have completed our discussion of the definition of the ROC, properties of the ROC, some of the properties of the Laplace transform, and a description of the properties of the Laplace transform with LTI with respect to LTI systems and several other aspects. So, this completes our discussion of the theory behind the theory and applications, and the properties of the Laplace transform, and the subsequent modules we will look at some of the examples related to Laplace transform, solving problems involving Laplace transform as it applies to the principles of signals and systems. All right. So, we will stop here. Thank you very much.